So, welcome everybody. This is the first research track of BPM. This is an incredible honor to start the dances. It's really wonderful now to see you all here connected. Today we are speaking with Cicilu.
And Claudio.
And yeah, you know, just like in the radio broadcast, isn't that the same feeling? So, right,
Great.
so today we'll have a session that presents a number of foundational papers in the area of modeling and monitoring. So they're very, you know, dense with contents, but we are sure that the speakers will make their best to make the availability of the contents as wide as possible and open. But you know what? We know you've been already through an intense keynote, which was marvelous. But also before the keynote, we had an announcement. So to let you leave the city, although you're unfortunately not yet in Spain, but I'm sure you'll go to Seville very soon after watching some of the images that you'll see today and the days that come. We leave now just to start off before the presentations, the stage to Adela, who will broadcast a video based on the Puente de Triana Bridge. So Adela.
Yes, I'm sharing my.
So this is the Puente at night. No.
Can you see something or no?
Yes, we can now see the Vimeo window on the browser.
Okay, and now it comes.
So we're standing in front of the Triana bridge, and the name of the bridge is derived from the fact that the bridge connects the Triana neighborhood with the center of Sevilla. It's a bridge which is already 200 years old, but it has a very famous predecessor, because in the 12th century, the Caliph here also tried to cross the river, but he wasn't able to build a bridge, so he used 13 boats, which he moored here and anchored here and connected to each other so people could cross the river here.
And this is actually an icon in Seville, and it's a very important bridge because we have a special week here, the Holy Week, which happens during the spring. And one of the most courage virgin crosses the bridge in a huge procession, and you can see the bridge really full of people, so crowded that you even fear that it can drop.
But it never happened, right?
No, no, fortunately.
Good.
And now I give the word back to Claudia.
Thank you. Wow. So that was one of the astonishing sights we can enjoy in Sevilla. So really looking forward to be back there as soon as possible. That's absolutely fantastic. So, right, after a breathtaking view of the Puente de Triana, we can start off the presentations. So I said, the presentations today would present papers that are published in the proceedings. For those of you who didn't have yet the chance, I would like to remind that the proceedings are open for all participants to download and read the papers. The papers are absolutely of an astonishing quality, so I would definitely recommend it, especially, you know, by the curiosity that is raised by the presentations that are coming. So to start with, we would give the stage to Marco Montali for probabilistic business constraints and his paper with Fabrizio Maria Maggi, Rafael Peñaloza, and Antti Alman. So Marco, can you confirm that you're connected?
Thank you very much, Claudio. Yes.
Thanks very much. So, stage is yours.
I hope you see my screen, right?
Totally, that's perfect.
Okay, so in the next 2 hours, I'm joking, obviously, 12 minutes, I'm going to talk a little bit about how we extended the well-known notion of temporal business constraints with uncertainty. Our topic of interest here is the one of conformance checking and monitoring. So with these two techniques, what we want to do is taking a trace that represents an execution of a process and combine it with a reference model so as to understand whether the two agree. In the case of monitoring, the situation is even more trickier because the trace is only partially known and we don't know about the future continuation of it. One observation is that usually the reference model against which we compare these behaviors is considered as a crisp model. And I will tell you what does it mean. Let me just briefly mention before that recently this was relaxed in a series of papers on stochastic conformance checking. The difference with our work being that there they were considering Petri nets or in general imperative process models. Whereas in our case, we are considering as a way to express the reference model, a declarative approach in which the process itself is represented as a bunch of temporal constraints. And what are these temporal constraints? These are simply constraints that relate activities over time and then separate the legal and the unlegal process executions declaratively. In particular, we adopted the declare framework. So in declare, you represent a process by using activities, which are these rectangles. And then you can decorate these activities with constraints. So for example, in the simple model that I'm showing to you here, we are declaring with this constraint that we want for each execution of this process to contain one and only one execution of the close order activity. This constraint here is called precedence and is a binary constraint. Is telling that before being able to accept an order, I need to have closed it already. This constraint instead is called a response, and it is dictating that whenever I close an order, eventually in the future, I will need to accept it. And this last one is called the not coexistence, is saying that within the same execution, these two activities should not both be executed. And what does it mean then that declare adopts typically a crisp semantics? It means that for a trace to satisfy the model, I need that all constraints are satisfied. And now if you take a look at the example that I'm showing to you here, the example does not make any sense. In particular, this constraint here is telling us that we have to close an order. These two constraints here are separately dictating that I will need them to accept and also to refuse the order, which will contradict then this not coexistence, which is telling that one should take a decision among the two. So then why would a user want to express this model? Because maybe not all of these constraints are actually crisp. So we may be in a situation where, depending on the execution, some of the constraints should hold and others instead should be violated. And this has to do with uncertainty, right? So for example, if I now go back to my model, the subset of constraints that I'm showing there should stay crisp because it's representing basically some sort of physical constraint that I want to enforce in my model, and I don't want to object to these constraints. So there will never be the possibility of accepting or refusing an order that has not been closed before. What about the other constraints instead? These constraints now should be interpreted in an uncertain way. And as said, this means that depending on the execution, some of them may hold and some of them may not hold. So take, for example, this response constraint here. When this constraint holds, it means that whenever I close an order, then I eventually accept it. When this constraint does not hold, it means that I close an order, but then I never accept it afterwards. So I leave free to do other things, but not to accept it. And now let's represent with a 1 the situation in which this constraint is satisfied, and with a 0 the situation in which this constraint is not satisfied, so is violated. If you now consider that this could be applied to all the uncertain constraints that we have in a model, this gives us 2 to the power of 3 possibilities, right? Because for each of these uncertain constraints, we may have that the constraint will hold or not hold depending on the execution. And you can see here what we call constraint scenarios, where each scenario represents a configuration in which I pick for each uncertain constraint, which one will hold and which one will not hold, okay? So for example, this scenario here is representing now a situation where I satisfy all the crisp constraints, I violate the response 1, and I satisfy the other 2 uncertain constraints. And for example, this scenario now is capturing the situation in which I close an order and then I refuse it and I never accept it. And so you see now from a single constraint model, I am giving rise to different, we could call them declarative process variants. Okay? And so now put yourself into this quite interesting situation. What we now can do is quantifying this level of uncertainty. So you see now that I'm putting numbers attached to these uncertain constraints, 0.8, 0.9, and 0.3. For simplicity, I'm now just focusing on exact numbers, okay? What is the intuition of these numbers? The intuition is to say, if I pick randomly a trace from a log, what will be the likelihood that this trace will satisfy that corresponding constraint or not? So you can see this as a sort of measure of conformance probability. Let me now detail this a little bit more. If I give you a log, what is the meaning of a crisp constraint? This is pretty standard. For example, take this one-to-one constraint. This is crisp, so each trace contained in the log will need to satisfy it, which means that each trace in the log will contain exactly one close order activity. What does it mean instead to discuss the conformance and the satisfaction to these uncertain constraints? Since we have a number here of 0.9, it means that in 90% of the traces in this log, we will satisfy the constraint, which means an order will be either accepted or refused or none of them. And now the subtlety comes into play here, because if I have a 0.9 as a number, this implicitly means that in 10% of the traces, actually, the constraint will not hold. And when this constraint does not hold, we are now implicitly characterizing a situation in which the seller, assuming that the seller is the one responsible for accepting or refusing, changes their mind. So accepts and refuse, and then maybe accepts again, and then refuse again. And now you see we are in a very subtle situation. We added this number, we have a very clear semantics, but what happens now when I put all these constraints together with their corresponding numbers? So now I just want to show that reasoning of these scenarios is tricky. First of all, let's just do plain logical reasoning as we do in normal declare. I already told you that if I take all these uncertain constraints to hold, I end up in a scenario that is completely meaningless, right? That is to say, scenario 111, the one in which we assume all the uncertain constraints to hold, is logically inconsistent. So we have to rule it out among the possible scenarios we have. But then there is also these numbers coming into play, so the probabilities. And for example, if you combine these two numbers here, you may immediately notice that their sum exceeds 1, which means we need to have some traces in whatever log we have that will satisfy both constraints at once. But by satisfying these two constraints and also this constraint here, we will never be able then to satisfy this constraint because this would lead to a contradiction. So implicitly, again, by reasoning on logical aspects and probabilistic aspects here, I end up by inferring that scenario 110, the one in which this constraint holds, and this constraint is violated, must have a non-zero probability to hold if I look into a log. So that said, we can approach this in a very systematic way by combining logical reasoning with probabilistic reasoning. The first step is to rule out all those scenarios that are logically inconsistent. And this I can do with plain logical reasoning, as I was doing this with declare, which just for those of you who are interested in the technicalities, is nothing else than a bunch of linear temporal logic formulae over finite traces. So I can do logical reasoning and understand which scenarios are consistent or not. For those scenarios that are inconsistent, since they don't have any conforming trace, obviously, they will have a probability 0. For those scenarios instead that are logically consistent, I can do probabilistic reasoning. And I don't have time to explain you how this is done, but basically we lift the probabilities that are attached to the single constraints into a probability distribution over the entire set of scenarios. And this can be done by simply translating this into a system of linear inequalities. We solve this system of linear inequalities and we get probability ranges. In this specific example, I don't actually get a range. I really get exact probabilities for each of the scenarios. And you see what is interesting now is that a logical consistent scenario turns out to have probability 0 due to the actual numbers that I have put here. Whereas the other scenarios get a non-zero probability. And as you may expect, globally, they give 1. Okay, so they exhaust all the space that we have. So now with this combined reasoning, we get understanding of each scenarios may hold in a log, and what is the likelihood that if I pick a trace from the log, this trace will end up in one of these scenarios. And I can use this directly to do a form of probabilistic conformance checking. How do I do this? Let's take this very simple trace in which I simply close an order and I don't take any decision. I can check the satisfaction for each single uncertain constraint in the model. Obviously, for the crisp constraints, I need to have conformance there. Otherwise, I would end up immediately in non-conformance. And now, in this specific example, this trace here is violating the first constraint because I have a close order that is not followed by an acceptance. I violate also the second constraint for a similar reason, whereas I satisfy the third constraint because I don't have acceptance nor refusal, so the two are not coexisting. And now you see here, I get the scenario. I can simply look into the table I computed before, and I get that the probability of this scenario is 0. So this means that the trace is not conforming. You can play the same game with a different trace, okay? In this specific example, you would end up into this scenario here, which has a non-zero probability. So it means that the trace is conforming, but in addition, I can also get as an output this 0.1, which is telling me, look, this is conforming, but is a very outlier behavior. So it's a behavior that you will rarely see in the process that is described by this uncertain declare model. And so you see, we're now ending up into a situation where we can explore these probabilities to give user feedbacks. And actually, I don't have time to tell you how, but this is really raised to the next level when we enter into monitoring. And monitoring really needs to reason on scenarios. And by reasoning on each scenario, we can also combine probabilities and give more refined user feedbacks. The thing that I have to stress now is that this approach has been fully implemented, whereas we are not yet into the empirical validation of this. So in particular, the interpretability of the measures that we can return to the user is something that is an open challenge. So now to conclude.
Exactly. Yeah? Thank you very much.
So now to conclude, I hope that I gave you at least a little bit of a glimpse about what happens when you start interpreting these constraints models under uncertainty, how you can reason logically speaking and in terms of probabilities in a combined way. There are various avenues of continuation here. From the technical point of view, if we adopt logics that are based on regular expression, I think we can now enter more into the line of work on stochastic conformance checking and have a declarative logical representation of that. And so this is something we want to look into. Another really low-hanging fruit that we want to explore is that once we have these scenarios and their probabilities, we can take off the shelf other approaches that have been adopted, like earth moving distance to align a log with a model, also in this setting. And to really conclude, if you're interested more into the logical underpinning of this approach, which is based on probabilistic temporal logics, we have a AAAI 20 paper. And if you're instead interested more in the intuition behind these semantics, you can take a look at our case forum 20 paper. With that, I thank you very much.
Thank you very much, Marco, for the presentation. It was very, very, very nice. Congratulations also for explaining the entire content in via example. It was very nice style. Thanks very much. All right. So, and being exactly in the mood, I failed to fulfill a constraint, which was let the people know how to ask questions, then present precedence constraint. So just to say it out loud, in case you wonder. So I see already Professor Vesque has raised his hand. So we can either raise our hand to give to let the organizer know that we want a stage for asking a question, or we can use the Q&A panel. You can see the Q&A button on the lower end of your screen on the left-hand side. Sorry. I would start with Professor Weske, who raised his hand. So I would ask him to unmute. 1 second. So.
All right, can you hear me?
Yes, perfect.
Yes.
Thank you very much.
Very good. All right, so excellent presentation. Very, very clear, Marco. Thanks a lot. It's just an observation. So you do allow traces in which you have both activities accept and refuse, and that will be around probably around 10% or something like that. And in these traces, I mean, it's really relevant if accept is before refuse or the other way around. So I was wondering about ordering constraints between these two activities.
Okay, so as you correctly pointed out, Matthias, we should probably refine this if you want to get into that aspect in the picture. So in Declare, for example, there is what is called a negation response that would tell you that after you do an activity, you cannot do another one. That would orient this forbidding a long time. And if you pair this with these probability measures, then you could get probably what you want. So in general, this gives me the opportunity to maybe explain a little bit more one aspect. These scenarios obviously are not singling out single traces. They single out like equivalence classes of traces or sets of traces that behave in the same way with respect to the constraints. So if you just take the example that I had, you would never be able to distinguish what you wanted to distinguish. That would require to refine the constraints that you're using. Now that we are exiting from the realm of standard declare, there is even more than the question whether the set of patterns that we have there for modeling are enough to express what we want. And you know, as a foundational person, I typically use declare as a simply graphical front end for something that is simply a linear temporal logic theory over finite traces. But you know, obviously an end user would never be able to write formulae directly. So it would be very interesting to understand whether, especially now that we have this probabilistic twist to it, new patterns would arise as important ones in terms of end users.
All right. Thanks, Marco. Thanks.
Thanks a lot. So we see there is a question from the Q&A from anonymous attendee. So I would let Cici read it. Thank you, Cici.
Hi. So the question is on about slide 22. So it says, 0, 0, 0 is a logical consistent with anything, right? So what's the difference between pause violation and possible satisfied?
Okay,
on
so
slide 2.
Yeah, so in the paper you would find the detail. So I mentioned at the beginning something that then I didn't have time to discuss, which is related to the fact that we are looking at once into conformance checking, but even more interesting for us is monitoring. Also because, I mean, philosophically speaking, I think conformance checking is very useful if you do it online, because you want to take measures if there is countermeasures or actions if there is a problem with conformance, right? I mean, checking whether 20 years ago my process was conformant is not so interesting. So when it comes to monitoring, you are observing now only a partial trace, and the continuation of this trace is unknown. And so now with this logical reasoning, what you can do is refine the truth value of a constraint that in my presentation was just a 0 or a 1. You could refine it into 4 values. I mean, there were various approaches in the literature, but the one that we adopted here is a 4-valued. And these 4 values simply mean you may have, first of all, that the constraint is currently satisfied or not, which is exactly what I was using during the presentation. But even more, suppose that the constraint now holds, you have 2 subcases. The first one is no matter how you will continue the trace, the constraint will continue to hold, or instead you may foresee that in a continuation, the constraint will be violated. And you can do the same for the case in which the constraint is currently not satisfied. You may have that no matter what you do, the constraint will stay not satisfied, or instead the case in which you may be able to fix this. And this gives rise to the different variants that you have been mentioned. So for example, if I don't want that the order is accepted and refused at the same time, once I do this, this violation is irrevocable. There will be no way of fixing this in the future. Whereas, for example, if we consider the response constraint, if I close an order and then eventually I expect to accept it, currently the constraint is not satisfied because there is no acceptance yet, but in the future, if I generate the acceptance, I will satisfy it. And that's now refined into the approach that we have here by combining these monitors with probabilities.
Thank you, Marco. That's very clear. I see another question from the attendees. Hugo, please go ahead.
Hi,
Hugo?
Yes. Thank you, Marco, for the presentation. Thank you so much. It's really, really interesting. I have a question regarding, I understand the part of logical reasoning, but how will you present this to the user? And I'm interested especially in the simulation part. Are you planning to code this into a probabilistic automata and the like? And the other part was, how does probabilities play on the infinite cases? So if you have an infinite trace, what would happen with constraints?
Okay, thank you, Hugo. There are various points here. Let me try to be short, otherwise simply kill me if I'm taking too long. So one thing that I have to mention probably that I could not stress in the presentation. Obviously, this is always a question when you throw in probabilities. Who is giving you these values, right? I'm not a probabilistic guy, so like I simply adopted here the logical approach. But we also have in a paper something very interesting. So you can actually mine these numbers directly from a log using off-the-shelf techniques. So if I give you a log and you take the usual support measure with constraints, how many traces in the log are satisfying a constraint and what is the total number of traces? If you compute this ratio, this is precisely the numbers that I was using. And some of you probably remember this problem that when you discover declarative constraints from data, if you accept constraints that have a support that is less than 1, you may end up in logical inconsistency. And we fixed that with Claudio and other people in a BPM paper. But if you instead attach these numbers to the constraints, you will never end up in inconsistency because you are reasoning with these numbers together with the logical aspects. So it becomes very interesting, but is also very detailed on the log. So these numbers will change if you get new traces. I don't think I have time to reply to the other parts. Let me just briefly mention that logically speaking, you would need to end up into very difficult automata, but not if the numbers are attached to the constraints as a whole. In that case, you can really separate the two types of reasoning as I did here. And so the automata that you are computing are the standard finite state automata that you have for declare.
Thank you, Marco. Thank you very much for this very interesting presentation.
That was indeed very nice that there were so many questions and so much interest gained. So that was the perfect opening for the research track. So
I'll be at the coffee at 3 o'clock, right? If you want to discuss this further.
Indeed, right? I was just about to know. Thanks, Marco, for anticipating that. Yes. So for those who are into this, you can take advantage of the coffee break with the others. Thanks, Marco, for participating.
Great. Coming up next, we have Daniel give us a presentation about the exact parameter-free algorithm for online process monitoring. Daniel, please go ahead.
Oh, thank you for the introduction. Can you see the screen?
Yes.
So in this presentation, we are dealing with online process monitoring, and therefore we assume an event stream rather than an event log. And on such an event stream, events are emitted over time. And for example, the first event tells us that activity A has been performed for a process instance identified by C1. The idea now of online conformance checking is that every time we see such an event, we compare the activities executed so far for a given process instance with a given reference process model. And by doing so, we achieve a real-time deviation detection. That means we detect deviations right at the moment they occur for an ongoing process. And this, for example, allows then a process owner to immediately take countermeasures, for example, if we detect deviation. And now the comparison between activities executed so far in a given reference process model is based on prefix alignments. Therefore, a short repetition about alignments. So first of all, and in general, alignments allow us to compare observed and modeled process behavior. And therefore, consider this simplified ordering process on the right-hand side. First, we can optionally execute create account, and then we have the choice between submit order and request quote. And furthermore, assume the trace A. So conventional alignment, the first row always corresponds to the trace if we ignore the skip symbol. And the second row always corresponds to a transition in the given reference model from the initial marking to the final marking. And an alignment is called optimal if it maximizes the synchronous moves and minimizes the visible model moves and clock moves. Now, next to conventional alignments, there's also the concept of prefix alignments, which are a relaxed version of the conventional alignments. Still, the first row corresponds to the given trace, ignoring the skip symbol, but the second row now corresponds to a sequence of transitions from the initial marking to some marking from where we can still reach the final marking. So if you consider the first prefix alignment, we just execute A, so we end up in P2, and from P2 we can still reach the final marking P3. So hence, prefix alignments are perfectly suited for monitoring ongoing processes. And now the question is, how can we efficiently compute such prefix alignments for an event stream? And therefore, consider the following example, which we use throughout the presentation. So consider the given event stream and the reference process model that we have seen before. So the first thing that we do is we create a so-called synchronous product net. And this is used to calculate prefix alignments. And the prefix alignment corresponds now to a sequence of transitions from the initial marking to a marking that has a token in P1 prime. So for example, we can execute the first transition that corresponds to a log move on A, and this would already be a prefix alignment for activity A and the given reference process model. And now the idea is that every time we get a new event, for this case, we extend the synchronous product net. So the next activity is B. So we extend the synchronous product net by a new log move on B, and also we add a synchronous move wherever possible. And once again, the next activity is C, so we extend again the trace part and also add synchronous move to the synchronous product. What you see is we just extend the trace part and we just add synchronous moves. And in contrast, the modeled part remains fixed. On this slide, you see on the left-hand side the three SPNs that I've shown you before. And on the right-hand side, you see the corresponding state space. And on this corresponding state space, a prefix alignment corresponds to a path from the initial marking to a goal marking or a goal state. And goal states are marked green here. So for example, we can go from here to there. So we synchronize on A and we found the prefix alignment. And what you will now see is when we extend the SPN, also the state space gets extended, but only states that are now goal states get new successor states. So we extend now the SPN, so we receive a new event, extend it, and you see these are now the goal states for the next prefix alignment calculation. And once again, we extend it again, and only previous goal states now get new successor states. So if we summarize these insights that we have now, only previous goal states get successor states when extending the SPN. That means only at the frontier we extend the state space, and newly added states, for example in this case these three states, they do not connect to old states. That means from a new state we cannot go back to an old state. The arcs only move forward to the newly added states. So going back to the first SPN, if we now want to compute a prefix alignment on the state space, we usually use the A* algorithm, which is an informed search algorithm that returns us the shortest path. However, given the short time of this presentation, we cannot go into all the details, but one thing is important to note for this presentation. And that is that A* algorithm maintains a so-called open set and a closed set. So in the open set, there are states that are discovered, and the closed set contains states that are fully explored and to which we already know a shortest path. And initially, only the initial state of the SPN is in the open set. And the idea now of A* is that in every iteration, we take the most promising state from the open set, move it to the closed set, and add all successor states to the closed set. So initially, we only have this state available, we move it to the closed set, and add the successor states to the open set. And now in this case, we can already stop because we have found the prefix alignment, because this is the most promising state. We can synchronize on A. So now we receive the next event, we extend the SPN, and hence also the state space gets extended. And what we see is that only states that are not discovered yet get new successor states, or states in the open set get new successor states. However, states in the closed sets are not directly affected by this extension of the state space. And now the main or central idea of our algorithm is that we now continue the search on this extended state space. So now we take this state, because it's the most promising one, we put it in a closed set, add the successor states to the open set. Now we can stop again because we found the prefix alignment for the trace AB. So what we have seen is that states in the closed set are not affected by the SPN extension. And we have seen that it is feasible to continue the search from the previous open and closed set on an extended search space. So putting things together, the main idea is every time we receive a new event, we continue the search on an extended search space, when we return in the end the prefix alignment. So a bit more in detail, we first receive a new event. So activity A has been performed for a process instance C. So we first load the SPN from the cache, we extend it by the new activity, as we have seen it before, and then we cache it again for the next search. And in case A is the very first activity that we have seen, we simply initialize the SPN. Then we take the SPN, load the open and closed set from the cache, and we continue the search on an extended search space. Then afterwards, we cache again the open and closed set for the next upcoming search, and we return the prefix alignment from where we can see if there was a deviation or not. And next, I'm going to present an experimental evaluation of this proposed algorithm. So what we did in the experiments, we used publicly available event logs, and then we simply iterated over each trace and emitted from each trace every activity on an event stream. So first we emitted A, B, C, D for the first case, then we went over to the next trace, we emitted B, D, and so on. This very simplifying approach for this experiments allowed us to avoid a more general problem in online process mining, namely the problem of deciding when the case is finished. So we always knew when the case ID switched, a case has been finished. And we compared our algorithm to two other approaches. The first one is OCCWX, where the X represents the window size. And this algorithm takes the previous prefix alignment, goes X steps back in the state space, and starts the search from there. And hence it does only a local search in terms, and not a global search, and hence it cannot guarantee optimality. That means it returns sometimes non-optimal prefix alignments. And we also compared it to OCC, which is a very naive approach that always calculates prefix alignments from scratch every time it sees a new event. And then, of course, optimality is guaranteed. So these are the results for the BPI Changelog 2019. And in the paper, you will find much more results. But given the short time, I only present these results here. What we first see is that the naive approach takes very long in comparison to all other variants. And what we see is that we increase the window size in the OCC approach, the computation time rises. If we now compare it to the number of traces with false positives, that means the number of traces where we received a non-optimal prefix alignment, we see first of all that our proposed approach, incremental A star, it guarantees optimality, so we never receive traces with false positives, and also the naive approach always guarantees optimality. And we see if we increase the window size, so we also increase the computation time, the better the quality gets. So there's a trade-off between quality and computation time. We also monitor two other parameters that are, first of all, the average queued states per trace and the average visited states per trace. So a queued state represents the states that has been added to the open set. And here we see incremental A star. So our proposed approach has the best efficiency across all other variants for the given event log. And a visited state represents a state that has been added to the closed set. And also here we have the best search efficiency compared to all other methods. So coming to the conclusion, what we have seen is an approach for online performance checking by incrementally computing optimal prefix alignments. And in comparison to other techniques, we are parameter free, so we don't need a window size or anything else. And we always guarantee optimality. That means we always return an optimal prefix alignment, and hence false positives with respect to deviation detection cannot occur. So the main contribution of this paper is that, first of all, that we showed, and we also formally proved it in the paper, that the continuation of the search is feasible on an extended search space. And we also have seen in the experiments that we are at least comparable, or in some cases even faster than other approaches, that do not guarantee optimality. And in future work, we would like to implement this idea in a real world scenario, and thereby we would like to address more practical challenges, like, for example, how to deal with limited memory, or how to deal with the high velocity of new events. And this is the end of my presentation. Thank you.
Thank you, Daniel. Again, imagine a rolling applause from more than 100 attendees. Thank you for this very nice presentation. We already see a question from the Q&A session from Ahmed. I will ask Ahmed to unmute. Ahmed, please go ahead.
Yeah, thank you very much. Thank you, Daniel, for the presentation. And actually, my question might belong more to the future work. So in a real life setting, events might arrive out of order. So even they were created in their source systems in order, but they might arrive out of order. So something like you can see the event of task or activity B. You receive it at your processor before you see that one of task A. So how would this affect your approach, or how this affects like this optimality and this parameter freedom of your approach? Thank you.
Well, first of all, if you just apply the algorithm as I presented today, you would just, so if they come in wrong order the events, you would maybe see a deviation because the reference process model would not allow this if they come in wrong deviation. But you could also, for example, apply some caching that you wait until you receive 2 or 3 events and then put them in the right direction. If you have, for example, a timestamp that you have some information about the correct order, and then you just apply the algorithm. So this would be an idea for a real world scenario now.
Okay, thank you.
Thank you. We see another question from Andrea. I will also ask Andrea to ask his question, which is related to I think to the evaluation.
Partially, yes. Thank you for your very nice presentation. I think that, so in my opinion, one of the differences between incremental and online is that in the online setting, you do not necessarily see the trace from its very beginning. So I would like to understand what happens if you observe a trace which has started already. So if you start to see events, not from the very beginning of the process, but in the middle of the process, would you get some reliable results or not?
So very likely not, because we assume that the trace starts in the beginning and ends properly. So for example, if you start right in the middle, so the first activity you see for a given case is directly in the middle, we would see in the prefix element before a lot of model moves, because this would not be allowed to start in the middle according to the reference process model. So the current form is not suitable for already started process instances.
Okay,
answer your
thank you.
question.
Yes.
Oh, thank you. Is there further questions? Please also use raise hand options or the Q&A options to ask your questions. I actually also have one question. I was wondering, we know that this is based using incremental A star and the fitness. So incremental A star is influenced by, for example, how fitting the traces are towards the model and the characteristics of the model. For example, if a model have more AND gates, then exploring the state will take more time. I was wondering, does this online incremental state space exploration also depends on the characteristics of the model and how fitting the log and the model is?
Yes, of course, because we use alignments, so we also have kind of the problem of the state space explosion problem. I guess that's what you mean.
Yes.
a very complicated model where a lot of parallelism is inside. Then you also have a lot of states in the search space. So, but this is a general problem of alignments in general. So this we did not tackle in this approach.
I already find very interesting that this allows you to incrementally online find the optimal alignments in N. Thank you, Daniel. Thank you for this very interesting presentation. Coming up next, we have, I still need to learn pronounce his name, André, from who is going to present PatroNet with parameterized data. Thank you. Andy, I will then use that. Please go ahead.
Yeah, you hear me, right? Okay, great.
Yes.
So
yes.
just a second. Right. You should be seeing now everything running,
Yes.
right? Perfect. Okay, great. So one more time, hi everyone. So I'm Andy, and today I'm going to present you our joint work on PatroNets with a couple of data-aware twists. All right, so let's go on. So I'm going to just say a couple of truisms that I probably would be even banished for, but so we all know that there is the data process dichotomy problem. And to solve it, we need to find solutions that, depending on specific tasks that we have at hand, try to balance between data and process components. Well, and such solutions, at least I believe that such solutions are usually sold under the term of data-aware processes. But so in general, when dealing with data-aware processes, we know how to model process components, right? So for the BPM community, it would be probably quite easy because you can use BPMN, UML activity diagrams, PatroNets, yeah, just and other useful formalisms. And on the data side, you also know how to model data. Although there probably we have slightly more choices. But after the models are done, so the main question is, what do we want from them? We just probably want that the data-aware process that we just modeled works well, right? However, working well is quite a broad term. And let me just say that we want to be able to analyze our processes well, and thus eventually guarantee that they do work well and respect specific quality requirements. But notice one important thing. So when you analyze data-aware processes, you need to consider the process evolution as well as causes and effects the process induces on the data. So we should always choose carefully the process components, process and data components, sorry, of the constructed framework for one simple reason. These components, they might not only affect the modeling aspects, but also completely change how we analyze the resulting process models. And in our work, we humbly accept the analysis challenge by looking into a framework that also allows to analyze data-aware processes and answers a very, I think, interesting question. So the question is my process going to respect given quality conditions or goals, no matter the kind of read-only data it runs on, right? So, and for that we propose a framework called catalog nets that is mixing, let's say on the process side, high-level PatroNets, which are, in our case, essentially colored PatroNets with fresh name generation, whose tokens carry type data objects from possibly countable infinite domains, which normally are used for representing the process volatile data. And on the data side, right, so we're mixing our high-level PatroNets with read-only persistent storage that can be queried using a powerful fragment of SQL. So I'm not going to go very much into the details of our formalism, but I'll just highlight a couple of features that I think are very interesting. So let's start with the control flow part. So we rely here on colored places, as in colored PatroNets. What is probably slightly different from the colored PatroNet approach is that our types have potentially infinite value domains, and they're equipped only with the quality predicates. So here, for example, we have type order, which is just potentially infinite set of order identifiers. Now, we also have another nice feature that we keep on borrowing from formalism introduced, I think, somewhat 14 years ago by Rosa Velardo, which are new variables, which allow us to generate globally fresh data. So here we have this new O variable on the model, which generates always globally new order identifiers. So now we go on and we look a bit into the data side, more of the catalog. So which is the catalog is a distinctive feature of this formalism, which is the catalog is a persistent read-only database that can be used to inject data into net tokens. So this is a very important thing. It can inject how, right? So and to inject, we actually use transition guards, which as opposed to, let's say, traditional correlated Petri net approach, they're having two functions now. So on the one hand, you can query the catalog and again take the data and inject into the net using the variables on the ARC inscriptions. And another thing which is more traditional is that you can filter the flow, right? Just using this transition guards. Okay, so now I'm going to show you a token game. So a favorite example that usually PetriNet people show to everyone. It's a small example, a part actually of a small example representing order to delivery process. I'm gonna start with a net that has only 2 tokens representing 2 trucks for delivering orders. So we have them in pink here. And each truck is carrying a plate number and the information about its type. So one is BT, so it's a box truck, and RT is the refrigerated truck. And also our net is having a catalog that consists of 2 relations. So we have the product category relation that stores, as it says, the categories of products, and another relation that stores information about the product type compatibility. So we start our token game by firing the new order transition. So this transition can be actually seen as an emitter transition. And it's going to generate, so first generated one order identifier. Now we fire it again, it generates another order identifier. And notice that these order identifiers will always be globally unique. So they're going to carry always unique values. Okay, so now we decide to add some fish to our order. Right, to add some fish, however, it's not enough for us to check the order, but it's also needed to check whether the fish category is actually present in the read-only database, right? And for that, we are checking with our transition guard. So I'm saying checking, which is, let's say, more common PetriNet slang, but actually we are querying the catalog relation for all the product categories, and we're picking up the fish category. And as soon as we have all the values assigned to our variables, we are firing the add item transition, and we're adding 1 fish item to order 45. And here we have it in the ready place. Okay. Now we proceed with paying the order. So it's very trivial, right? We paid the order, and now it's in the paid order place. And so now we would like to proceed with loading the order on the truck. To do it, we need to be sure that one of the available trucks is compatible with the type of the product that we have just ordered and paid, right? So for that, we do the same thing as we did with the add item transition. We're again checking in our read-only database, in our catalog, whether we actually have any trucks compatible with fish orders, right? And we see that actually to transport fish, you need to have a refrigerated truck. So for that, we are also checking our place with trucks. So the resources, right? The place that carries truck resources. And we see that, as a matter of fact, the T51YN truck is our guy. So we, again, merge everything together, and we loaded everything on our truck, and the truck is good to go, okay? So that was an example of the token game. But now let's go on with analysis thing, right? So what I mentioned in the beginning. And in our case, we rely on MCMT, that is a SMT-based model checker for array-based systems. The interesting part about MCMT is that it's one of the few model checkers supporting parameterized verification of processes with data. And this actually perfectly fits our scenario because here we would like to verify our nets running on any possible catalog that has a fixed signature. And notice that with respect to the catalog, not with respect to any possible marking. So this is also a very important clarification here. Sorry. So, just the analysis flow, what has to be done. So to analyze, we need first to translate, apparently, into an MCMT specification. Then, as soon as it has been, as soon as our catalog net model has been translated, we need to define a property that should hold our catalog net. In fact, it should not hold because we're performing a safety check. Thus, we are looking whether our net is safe against bad properties, right? So we'd like, for example, to check whether it's possible that our order to deliver a net can have a configuration corresponding to a situation in which a delivery occurs for an item that belongs to a not yet paid order. Okay, so, and the last step is obviously the verification, right? And to verify the property, as I mentioned before, we run the safety check in MCMT that considers all possible instances of the catalog. And I think it's also important to mention here that our catalog nets in general have different sources of infinity and unboundedness. And MCMT essentially can manage our model in its full generality, which I think is also a nice feature. So now let me talk briefly about how catalog nets relate to some PetriNet-based, state-of-the-art PetriNet-based models, which are used also for modeling, analyzing, and running data-aware processes. So I'll start with actually a formalism that Marco and I co-authored before. And this is the...
Sorry to interrupt, 1 minute left.
Right. Okay, so I just run through it. So compared to DBNets, it's a nice, rich formalism in which you have full power of SQL, full power of relational databases, but you don't really have running verification. And I think I focus more on this one and the next one. So this is ISML, Information Systems Modeling Language, which Artem and Jan Martin are going to give a tutorial on later on today. And here I think the similarities are in the net models that we're having. So they're quite similar, but they're using conceptual data model represented using ORM. And focus rather on modeling enactment, whereas we are actually just doing modeling and verification. And another thing which is interesting is the formalism of proclets. So proclets used for modeling sophisticated interactions between process instances by correlating data objects and exploiting sophisticated synchronization mechanisms. And catalog nets can be faithfully used can faithfully capture one of the fragments of proclets, exploiting just user reification approach. And given that, I think it will be also interesting to see how catalog nets can be used for verifying proclets or used in the verification backend of proclets. So just the takeaway message. It's kind of like giving a question. So whether you think that catalog nets is a sweet spot between different PetriNet-based data-aware approaches, that due to the lack of time, I skipped a bit. Nice thing here is that parameterizable is always a fort, right? So being parameterizable with respect any kind of data that you have in your enterprise is really cool. And a conjecture, so it's just a conjecture, we think that catalog nets without the catalog can be used actually in the intercase process mining. So for example, like multi-viewpoint models, right? So that is also something to think about. And in the future, everyone usually says we want to do benchmarks. So we also want to do benchmarks. And as a matter of fact, we're already doing them. And there are certain limitations that are still present in MCMT that we're also currently dealing with. There's a more on the more technical side. And I think, so it's just 10 seconds, sorry. The last thing that, there was something that we noticed in Proclets that we still could not support is the whole place operation. And we want to see whether we can actually enrich the catalog nets with whole place operations and see actually how will it affect the verification setting that we have. And that's it. Thank you very much.
Thank you, Andy, for this very interesting talk. Again, imagine a very big applause from 100 participants. So Derek has already posed a question. I will ask Derek to unmute and ask. Please go ahead.
Thank you, Andy, for the nice presentation. Very intriguing model. I like it. Raises many questions. I have one very direct one on the statement you made about the equality check, which catalog nets do not support, and you link it to verification. Do you think that supporting the equals in the synchronization mechanism, especially in the correlation check, you first kind of synchronize with a couple of items, you later want to make sure you synchronize with exactly the same items, is that making verification intractable? So is it making the model undecidable?
So this is what we cannot support in our setting, right? So let's say as domain experts from that area, we know what our verification setup can do. And our verification is based on backward reachability. And backward reachability does coverability, essentially. Yeah. And does accounting for exact elements that you would like to synchronize on is impossible. So it cannot just simply capture it. That's why we're saying a subset, because it's somewhat, the whole process is somewhat non-deterministic in the way, in the way that you would pick up your elements that you want to synchronize on. So you can just have, I don't know, 10 orders, 10 items in your order, and you would like to synchronize in a subset. This is easy to be done. So this can be captured also in catalog nets. But if you want to do the whole place, so you want to synchronize exactly on all of them, this is simply not supported by the framework of the tool, let's say.
Yeah, but so I get that. But if you say it's not supported by the framework, that's because if you would add support, just kind of you can't verify anymore because some.
So we don't know.
You don't know. All right.
Yes,
all right.
But that's let's say I probably should have said that this is more of a conjecture. So we could add that thing. We know that currently it cannot be done, yeah. But later on we need, let's say, to discuss that thing. So for now, it's not supported. It's impossible. Okay. But it's a very interesting thing to look into.
Yeah, thank you.
Can I briefly add something, Zizi?
Very briefly.
No, so Dirk, just to add on top of what Andy was saying, I'm not sure whether this would lead to undecidability in general. So I'm not sure how Proclets map to this, set of Patronets models that have been studied, on top of which you have these clear boundaries of decidability and decidability. For the model checker, I think the problem would be even in the general case of parameterized verification, because these things then mix up, would be really on the completeness of the verification. Because probably you could even add this, right? I think, Andy, as a modeling construct, but then you would never be sure that the runs that the model checker is generating are spurious or not, because to model what you want to model, you would need a for-all quantifier, and a for-all quantifier is only approximately handled by the model checker, you see? So,
thank
yes,
you.
It's having this kind of lossy semantics, let's say. Yeah.
Thank you, Marco. Thank you, Dirk. Thank you, Andy. The discussion is very interesting. Unfortunately, we have to cut off due to time reasons. I would really suggest you to take this further in the coffee sessions with the authors. I see another hand from Yamada. Please join them in the coffee sessions. again, a very big applause. And now I will give the floor to Claudio.
Up next, we have Anna Kalyankova, who will present her work on a framework for estimating simplicity of automatically discovered process models based on structural and behavioral characteristics, a joint work with Artem Poliviani and Marcello La Rosa. Anna, the stage is yours. Anna, it seems like you're still muted. Let's try again.
Hello everyone. Sorry, can you see my presentation?
Perfectly, thank you very much. And if we clear you.
Thank you. So hello, my name is Anna, and I'm going to present a framework for estimating simplicity of process models discovered from event logs. This is a joint project together with Artem Poliviani and Marcello La Rosa. So in information systems from various domains record the behavior in form of event logs. These event logs can be further analyzed and process models can be discovered. On this slide, you can see an example of a simple event log of a passport renewal information systems and two models discovered from this event log by the split miner and inductive miner algorithms. Different models discovered from this event log can be compared basing on their behavior and on their structure. To assess the behavior of process models, we can apply conformance checking metrics, and we can calculate the precision, the share of the model behavior that is also supported by the log, and recall that is also known as fitness, as the share of the log behavior accepted by the model. And here on the slide, you can see precision and recall values obtained using the entropy-based approach. And in these values, we can say that precision of the model discovered by the split miner algorithm is better, while the inductive miner algorithm produces a more fitting model that accepts all the traces from the given event log. Also, we can compare structural characteristics of given models, such as we can apply such metrics as number of nodes, ages, density, diameter, and others that are known as simplicity metrics. For instance, we could say that these models are equals in terms of simplicity because they have the same number of nodes. So they both have the same 10 nodes. However, although they have the same size, they present a different behavior. And we should also take into account if these behaviors they present can be modeled in a simpler way. For instance, the model discovered by the inductive miner algorithm accepts all the traces of the given alphabet of 4 labels, and this behavior can be represented in a simpler way with 8 nodes only. And this doesn't comply with the K-razor principle that says that entities should not be multiplied without necessity. And this should also be accounted when we calculate and assessing the model simplicity. And we should adjust our existing simplicity metrics in order to comply with the K-razor principle. We should compare our models to the models that describe the same behavior, but in a simpler way. To this end, we propose a general framework that accounts the K-razor principle by relating process models to other models that represent the same or similar behavior but have different structure. The framework is a tuple of 3 components. The first is a collection of process models. This component can be instantiated by Petri nets or BPMN models or finite state automata models or directly follow graphs. Then we have to include a measure function that defines a structural complexity of the models from the collection. So here we can use already existing simplicity measures, such as number of nodes and number of ages, diameter density, and contraflow complexity. And last, we have to define a behavioral equivalence relation over M. This can be by-simulation relation or weak by-simulation relation, trace equivalence relation, and topological entropy. So how this framework can be applied? For the model discovered by inductive miner algorithm, we can compare it to the model that describes the same behavior but in a simpler way. Generally speaking, we can consider model M star that belongs to M, and that is the simplest model, but from the same equivalence class defined by relation B as model M. And here we can define simplicity of model M as the relation of complexity of the simplest model M star from the given class to the complexity of the model we analyze. And here we can show that, for instance, the model discovered M2 by inductive mining algorithm gives us the value that is less than 1, while model discovered by split miner shows the best possible simplicity, because this is the way this particular behavior can be described with minimal number of nodes. So these are relative metrics that can be used to adjust the existing simplicity measure if we also will take into account the behavior of models. Now, to apply our approach in practice, we have to instantiate our framework. And for M, we selected a set of block-structured models with fixed number of uniquely labeled tasks. These models are discovered by inductive mining algorithms. Sometimes they're discovered by split miner, but not in all the cases. For structural complexity, we use two metrics: the number of nodes. This metric includes events, tasks, and gateways, and contraflow complexity, that is a sum of two numbers: the number of all splitting parallel gateways and the total number of all outgoing contraflow of all splitting or choice gateways. And to find behaviorally equivalent models, we use the notion of normalized entropy, that is function that defined on the set of languages, and for each language over the given alphabet it produces a number between 0 and 1, and the property of this function is that the more variability the model has, the higher is the entropy value. So for instance, the entropy of a sequential model is 1, while the entropy of the flower model the entropy of the sequential model is 0, because there is no variability there, and the entropy of the flower model is 1. In our settings, each process model can be represented as a pair of numbers, a normalized entropy and a structural complexity, and we can plot all the models as dots and estimate how far our new fresh model is from the simplest models. On this coordinate planes, we plotted oblong structured BPMN models with 3 tasks that have a minimal number of nodes in the first graph and minimal contraflow complexity. X-axis corresponds to the entropy value from 0 to 1, and Y-axis corresponds to a structural complexity, so it's either a number of nodes or contraflow complexity. So by plotting these values, we're trying to relate the behavior characteristics of models and their structural characteristics, and when it comes to assess a new fresh model, we can put the dot to this graph and estimate how far is it from the best case, that is a f function that the worst case, that is f plus function that shows the maximum possible complexity for the given entropy value, and f minus function is the envelope function that shows the best possible complexity for the given entropy value. And relating our model to the values of this function for the particular entropy will allow us to estimate and to produce a relative value showing if our model presents the given behavior in the simplest way. Next, we will demonstrate this approach by applying it to process models discovered from real-life event logs. We have analyzed process models discovered by inductive mining algorithm from real-life event logs. On this slide, you can see the worst case and the best case envelope functions. These are f plus and f minus functions. We constructed them empirically based on a pre-generated set of BPMN models with 6 tasks. And note that it is computationally expensive to exhaustively construct the set of all BPMN models with 6 tasks, so we randomly generated only some of them and approximate the envelope functions. So the envelope functions themselves can be defined using splines as well as can be piecewise functions. So let us consider a model that is called M8. This model was discovered from a real-life event log. And here on the first plot, you can see that it is above the worst case function. So this model is shows the behavior in a complicated way. And indeed, if we will take a look at this BPMan model, we will see that actually this is a flower-like behavior, and we can draw manually M'8 model that represents exactly the same behavior, but in a more compact way if we talk about the number of nodes and contraflow complexity. And indeed, you can see that M prime is below M8. And if we will try to calculate the relative simplicity matrix, we will see that in terms of number of nodes, M8 prime is the best possible model because it lies on the best possible case, while M8 is even above the upper function, the worst
Anna,
case function. And
head towards conclusion now. Thank you.
Sorry?
We should head towards conclusion now.
Oh,
So,
I'm sorry.
Yes.
We also analyze different models. So here you can see examples of the models that M2 and M1 that have the same complexity but different entropy values, and we also were able to assess their simplicity. And M1 allows for more behavior but has the same number of nodes, and this is why its relative simplicity value is higher. As the future work, we plan to developed an approach for analytical construction of envelopes for different classes of process models. And we would like to consider a broader range of process discovery algorithms. So also, we would like to explore the approaches for approximation of envelopes so that we will have a more precise approach. And we plan to develop a tool for simplicity estimation for different instantiations of this framework. So thank you very much.
Thanks a lot, Anna. Sorry for hurrying up towards the end, but it was a very lovely presentation. We would have joined to listen about, to know more about it even further. And indeed, we see already 2 questions asked in the Q&A and the raised hand from the attendees. So let's start. Hugo, would you Hugo, would you unmute your microphone, please, so that you can ask your question? Hugo Lopez. Okay, if not, then we can go ahead with Andrea Buratin.
Hi.
Thank you, Anna, for your nice presentation. I was just wondering if there are any preconditions to use this metric in order to have some sort of fair comparisons of the result. Because I have the feeling that this metric tends to give more advantage to those algorithms that are producing block-based structures, and tends to give more disadvantage to techniques that introduce loops. So I was wondering if there are any, if you thought about any topological preconditions that mining algorithms should meet in their results to have, fair comparisons.
Yeah, thank you. That's very nice question. Yes, so we do compare loops within our block structured models. But we still consider the finite set of models. So M is finite because we do not allow loops to be infinitely nested. So we do have a limited contraflow complexity here, and this can be considered as one of preconditions if we want to consider the worst case F plus function. So yes, we do consider the loops, and I think that the other part of your question was about if this approach fair, and basically we also played with the generator, producing exhaustively all the possible models everywhere where we could, and there are so for this particular instantiation of the framework, we discovered some dependencies between behavioral and structural characteristics of the models. And these dependencies allowed us approximate these envelope functions for for higher numbers of n, so for greater numbers of nodes and labels in BP-man models. So yeah, but in general, yes, of course, much depends on the instantiation. So for this instantiation, we exhaustively constructed all the models and found these relations. If we will, so maybe, what other models do you suggest to consider? We do consider the loops.
Yeah, no, I think you sort of answered my question already. I was more thinking about I mean, as you show, for example, the split minor, which has some specific kind of structures that is going to extract, whether that would be favored or not. But I think you answered already, so thank you.
Thank you.
Thank you. So now I would hand the token over to Ugo, who's now unmuted.
Yes, I found the button. Sorry, thank you. Thank you very much for the presentation. I think it's really nice, and I think this framework of simplicity you can apply not only for discover, but in general to measure, to dig into different process models. My question is more regarding if I want to generalize this to other models that do not, other process models that do not depend on control flows, like for instance, what we saw on the first presentation with probabilistic declare. What would be your thoughts on that? Can we somehow have a simplicity relation that does not depend on control flow to that matter?
Thank you very much for your question. So this is a very good question. The basic model that lies behind the entropy is deterministic finite automaton or finite state machine. And if we will be able to represent all our declarative models as a set of constraints within DFAs, within automata models, then we will be able to compute the entropy and we will be able to relate their structural and behavioral characteristics. So, but yeah, that's a very good question. So thank you so much, because yeah, within the conformance techniques, we usually we can represent models as DFAs. So why not to consider this approach as well? Thank you.
Thank you.
Right, so we have the very last question from Mohammad Reza, who raised his hand. So,
thanks for your presentation, Anna. In most current simplicity measures, it's usually opposite the complexity of the process model, but I guess it's not the case for your measure, because, for example, if we have only one process model for different event logs, maybe the value of simplicity could be different for different logs. How do you position your current measure compared to other complexity measures in the literature? Thank you.
Right. The idea is to relate model to its own behavior, not to the behavior recorded in the event log. Why? Because for this, we have precision and recall of fitness measures if we want to relate the model and the log. So what we're doing here is we're just trying to understand if this model represents its own behavior in the best possible way without relating it to the log.
Thank you, Anna. Yeah.
All right, so thanks very much. So we're already running a bit out of time. Thank you very much, Anna, for your presentation. Thanks to all the speakers, and a big applause to all of you. Thanks very much, guys, for joining us. Also for resisting like 10 minutes later than the expected end of the session, but this is a trick we can play with the online web, conferences, we hope. Anyway, so coming up right after lunch, we have research track with session 2, BPM4 session 2, also blockchain forum keynote, and the first tutorial of the conference. So the program is very rich. So enjoy your break and your lunch. And again, thanks again to all the participants. All this session has been recorded and will be made available to all of you who could not attend the entire session or just want to enjoy the replay of it. I want to say thanks also to Adela being behind the scenes, and Cici, who's been with me in this session. Thank you, Cici.
Thank you. Thank you. I will also thank you too, Claudio, for this very nice love radio style. Also thank all the participants. See you after the lunch.
See you. Bye.
Bye.